Welcome back to our lecture series on the subject Material Science and Metallurgy. In today's lecture, we talk about ferrous alloys, particularly the cast iron, that is white cast iron. In the previous lectures, we have seen grey cast iron, we have seen ductile cast iron. Now, in today's class, we will see white cast iron. So, if you recall, in 1 minute, so grey cast iron. So cast irons are classified based on the microstructure, and grey cast iron, which is comprised of graphite flakes in its microstructure, and which is basically indeed the root cause for its properties. And ductile cast iron, which is again, if you look at the microstructure, graphite is present in the form of spheroidal or nodulized form, because of which it is offering excellent properties in some areas where general cast irons are not able to do. So ductile cast iron, we have seen that it is having properties of steel as well as the general characteristics of cast iron. Now in today's lecture, we will talk about white cast iron. So we will be covering its composition, its microstructure, properties, limitations, and applications. And we'll, towards the end, we summarize and discuss the key takeaways from the lecture. So white cast iron is a hard, brittle cast iron. It is hard and brittle cast iron where carbon exists entirely as a cementite instead of graphite. As just now discussed, grey cast iron comprised of graphite, and ductile cast iron is also having graphite, which is basically coming from the decomposition of cementite. But in the white cast iron, that reaction, we are not allowing that decomposition process, and we are ensuring that cementite remains in the material as such. So when cementite remains in the material as such, so cementite is very hard in its nature and it is also brittle in its nature. So in the cast iron, this particular cast iron, white cast iron, which is hard and brittle, which consists of carbon present in the form of cementite. The key feature is there is no free graphite here. So if you look at the white fracture surfaces, it is basically there is no presence of graphite here, and so the carbon is present in the form of cementite. And when you cut the material, and you can able to see that there is a white fracture surface. So because of this white appearance, this material is called white cast iron. Because of their white appearance in its fracture surfaces, this material is called white cast iron. What is the formation condition? When does this cast iron can be formed? So when they are cooled very fast, and also when you are having very low silicon content, which is less than 1%. In the previous cases, we have seen silicon is ranging from almost 1 to 2.8%, right? So in this, and we have also discussed that silicon is the primary reason for graphitization, right? The formation of it is a root cause which promotes the graphitization. It is a formation of graphite. So now in this case, graphitization reaction that is not promoted. That's the decomposition reaction is not promoted. So that is when you have very low silicon content and when you cool very fast, then you can form this white cast iron. If you look at composition, so carbon is present between 1.8 to 3.6%, and which is having fully combined iron carbide cementite Fe3C. Carbon is present in the iron carbide cementite only. And silicon, it is not 1.9, which is less than 1 basically. So silicon is ranging between 0.5 to 1%. So it is deliberately kept low in order to prevent the graphite formation, in order to prevent the decomposition of iron carbide. It's also having manganese, small fraction, 0.2 to 0.8 percentage of manganese, which basically stabilizes the cementite. So in the previous lectures, we have seen that iron carbide is a metastable compound. It is a metastable compound we have seen. So it is not stable, and so it is decomposes or dissociates, especially when it is present with the silicon. So this compound will be stabilized by the addition of manganese here. So manganese is required to stabilize the cementite. That's why we are adding manganese here. And in addition to these primary materials, we will also have alloyed variants, basically to promote the properties of overall material, cast iron. So it has been combined with nickel chromium. It has been alloyed with the nickel and the chromium. So hence this cast iron is called as nickel chromium white iron. It improves primarily the hardness and corrosion resistance. Hardness is anyway coming from the cementite, and further it can be improved by the addition of nickel. And chromium is known for its corrosion resistance property, to bring in the corrosion resistance property in the metal. So we'll be adding chromium to the material. We have seen this, we have discussed this in the case of stainless steel. Very high amount of chromium, if you recall, 16 percentage of up to 16 percentage of the chromium is being added to the stainless steel, and that is a prime reason why steels are offering excellent corrosion resistance. And we have another variant that is very high chromium white iron. So chromium component is very high. High amounts of chromium has been considered in the white iron, that is called high chromium white iron, which offers excellent wear resistance properties. Right. So if you look at the microstructure, so microstructure, you can see the light cementite regions here. Light cementite regions. All these are like cementite regions. These are cementite regions, and which has been surrounded by the paralytic matrix. These are the alternate layers. You see the alternate layers. So this is basically a paralytic nature. So this is a paralite here, and this is a cementite. Cementite region. So this cementite is basically surrounded by the ferritic or paralytic matrix. Here there will be no nodules here. Sorry. So there is no nodular structure here. So if you look at the classification of white cast iron, so it can be present in the plain white iron where there is no significant amount of alloys like nickel and chromium is not been added here. So that is called plain white iron, which is used for malleable cast iron feedstock. So for malleable cast iron, the starting material could be your plain white cast iron. Okay. So primarily it finds its applications over there. Then we have nickel hard iron. So nickel chromium cast iron, as we have discussed. So nickel is present between 3 to 5 percentage of nickel and 1 to 4 percentage of chromium is been present. They find their applications in slurry pumps and crusher lines, where they take up a huge amount of wear resistance is required, as well as high hardness is also required. So in such applications, we will use this nickel hard iron or nickel chromium iron, nickel chromium white cast iron. And we have another variety as discussed, that is a high chromium white iron. That is where chromium is ranging from 12 to 28 percentage. It is very high, even higher than the stainless steel composition. So 12 to 28 percentage of amount chromium is being added to produce the high chromium white iron, which is where cementite is being replaced by these carbides, M3C3 carbides. So cementite is M7C3 carbides. It is even harder than the cementite. If you look at the properties and compare all these three varieties, what we have seen, plain white iron, nickel hard iron, and high chromium white iron. The hardness, Brinell's hardness number, BHN. So plain white iron is ranging from 400 to 600 BHN. Then nickel is little higher, 550 to 700, and high chromium is further higher, 600 to 800 BHN. In terms of strength 200 to 350 MPa, and nickel hard iron it is 300 to 500, and further it is being high chromium, it is high strength 400 to 600 MPa. Impact resistance. Impact resistance is very low in the case of plain white iron. White is very low because of the presence of Fe3C, which is very hard in its nature, and also it is very brittle in its nature. Because of its brittleness, its impact resistance is very low. So it's very brittle and hard because of due to the presence of iron carbide, and because of that, in turn, its impact resistance is very low. This is to some extent it has been improved. Impact resistance relatively it is improved from plain white iron, and since these Fe3C is been replaced with because of high content of chromium, it has been replaced with M7C3 carbides. Its impact resistance has been significantly improved here. So always you see the hardness comes at the cost of toughness. So there is a trade-off between hardness and toughness. So there is always you find it here. And if you look at other properties, so cementite, which precipitates precipitates from the melt form, which is relatively larger particles, they increase the bulk hardness of the cast iron. Since carbide makes up larger fraction of the material, white cast iron could reasonably called as cermets. What are cermets? These are basically ceramic and ceramic plus metal. So we call it cermet because ceramic. Why it is ceramic? Because of carbide, Fe3C. Because of Fe3C, it is the ceramic part, I would say, and metal because of basically the presence of iron. Right. So this white cast iron, it can also be termed as cermets because of large portion of carbide. So due to its large masses of carbide, white cast iron has excellent resistance against wear and abrasion because of high hardness. It is also offering excellent wear resistance as well as abrasion, which is basically ideal candidate for mining and cement industries. The crusher lines applications in mining and cement industries, these where we require excellent abrasion resistance as well as the wear resistance for its tools, right? So these white cast iron finds their applications, primary applications in the mining and cement industries. They also offer excellent compressive strength, which is 3 to 4 times higher than the tensile strength. Its tensile strength. They are also having limitations such as ductility, since it is very hard material. So ductility is very low. So it will not bend, but it is deforms like a plastic. So it is catastrophic failure can be expected from the white cast iron materials, white cast iron components. It is, since it's very hard in its nature, so it is nearly unmissionable. It is almost unmissionable, but it can only be grindable. So we can only grind and remove the very small amount of from its surfaces, but it cannot be, or it is highly challenging for machining such materials. It offers a very poor thermal shock resistance. So if this component suddenly put it in the thermal environment, like higher temperature environment, so it will fail because its resistance, thermal shock resistance is very poor. It will crack and then it will fail abruptly or catastrophically. So these are certain limitations that we have with the white cast iron. And if you look at the applications, as we have discussed, mining industry and cement industry are the primary applications where it has been used for crusher jaws and ball mill liners. It has been used in the cement industry. It is used for grinding rollers and slurry pump parts are also manufactured out of white cast iron. And in the railway segment also, it finds its application in brake shoes. So brake shoes where you require very high abrasion and wear resistance, they find applications. Brake shoes is the one component in the railway segment. In the agriculture, we use it for plowshares and tillage tools where it need to dig the land. So in these applications, white cast iron can be used. So your tillers like JCB and earth movers are there. No? So those tools are being basically manufactured out of white cast iron. So have you ever seen a rolled rock crusher in the crushing mills? So basically their teeth are made out of white iron because of their excellent wear resistance and abrasion resistance and its hardness obviously. But there are challenges, certain challenges are there, and always this is the cracking risk. During its solidification, because of their high hardness and brittleness and low ductility, they tend to find cracks during the solidification. So casting is little challenging, relatively challenging when compared to other cast irons. So summary, if you look at the summary, what we have discussed, since there is no graphite here and carbon is present in the form of cementite here, so you can find the extreme hardness in the material and it comes with a cost of brittleness, which is undesirable in its nature. And alloying with the chromium and nickel will enhance further, you can enhance the properties like wear resistance and corrosion resistance of the material. And these material finds their primary applications in the where abrasion is high requirement. So abrasion resistance components like crusher mills and mining mills and brake shoes, you find these applications, primary applications. So we call white iron as the glass of metals because of its very high brittleness, which is basically hard, but it goes with a coat like handle with care. So I have used these are some of the references that I have used for making this slide content. So I'm leaving this question for pondering your brains. So that is, why doesn't white iron rust as easily as gray iron? Why doesn't white iron rust as easily as gray iron? Already we have discussed about it. Cementite is more corrosion resistant than graphite. This is a hint that has been given. So your responses, your answers, you can drop it in the chat. So with that, I'll conclude this lecture and we will rejoin in our next lecture on the remaining topic in the cast iron, that is malleable cast iron. Thank you.